Hello and welcome to this podcast. We're going to look at the second part of the circular motion and gravitation unit, which is obviously the gravitation section. And we're going to start with a look at Newton's laws of gravitation. This is one of the shorter parts of the IB course, so we should move through it quickly. And before I begin, let me just be clear that this is about Newton's law of gravitation. Now, that is very interesting from kind of a TOK aspect almost, because why am I teaching you this given it's not true? Well, it's not true. I mean, Newton's law of gravitation has been completely replaced by Einstein's theories of how our universe works and gravity. But it's still useful. It still can be used to make good predictions, and it's really a good example of a step on understanding. If we try to leap straight into Einstein's rules and laws, it wouldn't work. It really wouldn't. So you might be interested and curious, and things like the black hole, which this image is meant to show, really do need Einstein to explain how they're happening. But it's still useful to consider the Newtonian perspective. Now, what is gravity? Gravity is a force, one of the four fundamental forces, particularly in this classical view. And it's a force that's most important once we get to large scales. The two nuclear forces, the strong and weak nuclear forces, we only need to worry about inside of atoms. And if we have a sort of a Greek view of atoms as being small, indivisible things, which is true most of the time, okay, for all of chemistry, we can think of atoms as just being immortal little balls. Then we don't need to worry about those two forces. Electromagnetism is incredibly important. Every time you think you're holding something or touching something, what you're really doing is just experiencing the electromagnetic forces of the electrons, and that is needed to explain what's happening there. But on large scales, electromagnetic forces don't tend to have much effect because they rapidly become neutralized. For all of the positive charges, there's always going to be plenty of negative charges somewhere close by. Only on small scales can we sort of separate them out. And so on larger scales, it really is just gravity which determines the shape and the future of our entire universe. It really is. And that is because gravity is always attractive. Unlike electromagnetism, it doesn't have a push and a pull. It doesn't have a plus and a minus. It always works in one way. It adds together. So the gravity of a galaxy is made from the gravity of the planets and stars, which is made from the gravity of the rocks and gas, etc. But as you move out in scale, it always adds together, it always gets bigger. And it's infinite in range, okay? So it will always have effects over very, very large distances. All those are true. What's also true, though, as we'll see later, is it is a very weak force. So even though it's a very dominating force, it stops us floating away, it keeps our planet together, it keeps our galaxy more or less in one piece, it is still a very weak force compared to the others. If you think about it, a little magnet, if it's hanging on to a piece of metal, is stronger than the entire planet, which is trying to pull that magnet down. Gravitational fields, we've talked about the concept of fields in relation to electricity. It's the same idea, really. There is a gravitational field which permeates the universe, at least that's one perspective. But we don't really need to worry about it too much because all we can think about from a Newton's perspective is pairs of objects, okay? There are as many pairs of objects as there are objects in the universe, and the force exerts between those pairs. And we'll obviously at IB diploma level, we'll generally keep this as simple as we can and just talk about a single pair of objects. For example, the Earth and the Moon, or for example, the Earth and an apple. Newton's universal law of gravitation, the interesting parts about it is that it is universal. One of his great breakthroughs in the 1660s when he was thinking about this was he realized that it's the same force that applies here on Earth, pulling apples to the ground, as applies to the moon, holding it in orbit around the Earth and the Earth around the sun. At the time, this was never a really obvious idea, the fact that you had these laws which applied everywhere. Now it's an important principle in physics, the cosmological principle, that the same laws of physics apply throughout the universe, and they do not change over time. They do not change with space, place, or time. We can draw field diagrams like we can with electricity and magnetism, which depict what's going to happen in a gravitational field. These are, if you look at a big enough scale, almost always radial, like this one. Although, of course, if you zoom in, they can appear to be sort of parallel. So a gravitational field inside a room, all the field lines will be pointing sort of straight down towards the floor. But that's really just a product of zooming in on a very small patch of what in reality is a radial field. The arrows show what will happen to a small test mass. And they're always going to be pointing towards the bigger mass because that's gravity. It's always attractive. The actual Newton's universal law of gravitation obviously is about the relationship between the forces and the other factors being the masses of the objects and their separation. That's it. It's pretty simple, really. It doesn't matter what the medium is, it doesn't matter what the type of object is, all that matters is the masses of the objects and how far away they are apart. Force is proportional to the product of the masses, the two masses multiplied together, and inversely proportional to the separation squared. It's another example of an inverse square law. To convert it from a proportional to relationship to a equals equation, we need a constant. And so we have big G. So big G is the number that we plug in to make our units work and to actually calculate force. It's one of the universal, the constants that you will find in your data booklet that was actually least well known for a number of years. It was very difficult to measure because it's such a weak force. People tried hanging threads, masses on threads near mountains to see if that would create a noticeable deflection from a sort of sideways force from a mountain. Nah, far too small to measure. It took Cavendish in the late 18th century, very late 18th century, using a method where he shone rays of light onto a mirror attached to a string. That string suspended a bar with masses on the end, and when those masses were placed near other masses, the purple ones in this diagram, it made the bar rotate slightly. There was a tiny turning force. And that torque, that tiny turning force, could be measured by shining a ray of light on that mirror and then bouncing it off and then it travelling a long distance and being able to see how that ray of light, sort of reflection, moved, reflecting the very tiny movements of the rotation of the wire. And so a value of G can be calculated 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared, which is a very, very small number. Two 1 kilogram masses 1 meter apart will have a force of 6.67 times 10 to the minus 11 newtons. Pretty small force indeed. Another thing that Newton realised, in fact, he kind of invented calculus as in order to be able to demonstrate this, is that although the force of gravity is generally because of the things that make up an object, so the gravitational force of the Earth comes from all of the rock and all of the other things that go into the Earth, mathematically it acts as though it's acting on one point. And we call that point the centre of gravity, or more commonly the centre of mass. And so when we're dealing with something like the Earth and the Moon, we don't have to worry about the actions of all the different bits of rock of the Earth and the different bits of rock on the Moon. We can just draw a single arrow coming from the centre of the Earth and the centre of the Moon, and that works. Okay, that doesn't mean there is a big on-off switch, gravity generator in the middle of the Earth and the Moon. That's not how it works. It's just a mathematical tool, but mathematically it does work, and it makes our life a lot easier. And just to finish off with, let's look at a couple of a use of that equation. Let's combine F equals gmm over r squared with Newton's other area, his laws of motion, acceleration, F equals ma. So if we drop an apple, then we can calculate its acceleration by the force acting on it, ma, and we can calculate that force using gmm over r squared. So to combine those, we get ma equals gmm over r squared, and obviously the little m's, which is the mass of the apple in this case, cancel. The acceleration is just big G, big M over r squared. So the universal gravitational constant, r, how far away apart they are, and big M, the mass in this case of the Earth. And it doesn't matter what little m is. It doesn't matter if it's an apple, it Doesn't matter if it's a person, doesn't matter if it's a spaceship, doesn't matter if it's the moon, it doesn't make any difference. And the acceleration will be the same in all cases. It just depends on the mass of the Earth and how far away the two objects are. Plug some numbers into that. 6.63 times 10 to the minus 11, big G. 5.97 times 10 to the 24 is the mass of the Earth in kilograms. And 6.371 times 10 to the 6 is the distance from the centre of the Earth, which is where we said, the centre of mass, where we said the gravity appears to be acting from, and the surface. It's the radius of the Earth on average. 6,371,000 kilometres, 6,371,000 meters, sorry, or 6,371 kilometres squared, because it's r squared. If you do all the maths, you get 9.81 meters per second, which is meters per second squared, which is a number you should probably recognise. We'll come back and look at that equation in a little bit more detail in the next session or the one after that. Thank you very much.